welcome. My name is Max. I've been working in the Sensor Edge Cloud Hub on the topic embedded green AI. And yeah, we've looked into how to benchmark the energy requirements of AI. And yeah, today I'll give you an introduction to the topic of energy efficient embedded AI. Yeah, so let's start. So if you look at the whole spectrum of computing hardware that you could use to run AI, to deploy AI, there's a huge spectrum. Every hardware has its own advantages probably, but we are really focused on deploying AI onto microcontrollers. And here one major advantage is that they are really low powered devices. They require less energy than bigger hardware. Okay, battery? Oh yeah. We've already talked about a lot of the advantages in Silvia's talk. You've mentioned already some of them, but I want to recap them maybe again. So one major benefit is that embedded AI, especially compared to cloud AI, is way more private. Since you don't have to send the data and communicate it to some external server. And yeah, you basically get data security for free. And second, it is fast. And by that, I mean not that the hardware itself is computing way faster than cloud hardware, but you don't have the detour via communication, waiting for a server to respond. And yeah, this makes it way more predictable and offers a lower latency. Next, especially when you're working with microcontrollers, these are tiny devices. They fit into almost any existing product. And lastly, since they are really low-powered devices, they force us to be by design kind of energy efficient. And yeah, that's the main advantages of embedded AI with microcontrollers. Well, on the other side, there are also challenges. And the major challenge here is that currently AI models, they are known to be computation intensive, large in size, they require a lot of memory. And on the other side, we have our hardware capabilities. Here, we are really restricted in the memory and also the computational power. So the question is, how do I get my models, which, for example, these on the left are for image processing. They are not large language models or any by far, but they're still at least 13 megabytes, for example, MobileNet V2, which is already designed to be efficient, but it's still way too large in its vanilla form for the hardware we are working with. So the question is, how can we reduce the size of these models to make them fit on our hardware? And the answer here is deep compression methods. And what that is, I'd like to explain you by showing you kind of the main development workflow that we use to develop embedded AI solutions. So let's imagine you have some problems, some tasks that you would like to solve with AI. Now, you start by collecting some data that you want to use for the training. You settle on a basis model. This could be, for example, the MobileNet V2 we've just seen. And then you have a bunch of so-called hyperparameters. They are kind of all the small design decisions that you have to make to get to your final model. And you kind of have to tweak them just the right way to get the most and the best solution. I think, was there a question? No, okay, sorry. And finding the right hyperparameters it's not an easy task. Normally you do this in an iteratively process where you start with an initial guess and just see what's really working. So let's say we settle on the first setting of these parameters and start training. So we train our first model, and during training, normally you can apply pruning. model pruning is nothing more than during the training at several points of time, you look at all the weights and all the structures in your architecture, and you use some heuristics to decide which of these are not really relevant, which of them do redundant tasks or are just not important, and then you can kind of cut them out, you can prune them out of the architecture, and by that, if this is done right, you don't really hurt the model too much. You can still decrease the loss and continue training, but at the end you will get a even way leaner model. For example, here, if you look at this plot, we'll reach a decrease of 60%. And yeah, that's not the only method we can use. After training, we can also apply model quantization. Model quantization is nothing more than we reduce the number of bits we use to represent all the values we use for computation. So this can be applied to the weights of the network. It can be applied to the input, to the activations. And by that, we again get a decrease in size by a factor of 4. And normally you don't lose a lot of accuracy. And the last step would be the model conversion. We're really still in our development environment, but we need something that we can actually execute on our target hardware. So we need to transform our model into an executable C code. And after we've done through all these 3 steps, we end up with an executable program where we actually know the memory requirements, the RAM, ROM, we know the accuracy of our model, and we know the number of operations that we have to perform for a single inference. And these are kind of the objectives we want to optimize. And since it's not a single objective, we're in the realm of multi-objective optimization. So kind of looking for the right hyperparameters to maximize all these or minimize all these objectives. And yes?
On the last slide, you talked about the model quantization.
Yes.
You do the downscaling for the whole training? Do you downscale the input data or just while the pipeline is running?
You mean with downscaling quantization?
Yeah.
You can apply it to the input as well, yes.
Okay.
So you can, during training, you probably use, sorry?
And the accuracy stays the same?
It does decrease slightly, but often it's not, it's a good trade-off because not only the model gets smaller, also the execution of the model is faster.
Oh.
That's another benefit here. So it's always worth it, especially if you're working on embedded systems. So I said the hyperparameter tuning is kind of an iterative process. So let's say we've run this 100 times. Then we end up with something like this on the bottom here, where we have multiple models which are to some degree optimal. This is called a Pareto front. So for all the red dots here, you can say there's no other model that dominates these models, since either there's no model with a higher accuracy and both lower memory requirements. So how do we settle on which of these points should we take? And this is kind of a still difficult question, but often this depends on the use case. And you could, for example, say, I already know I want to deploy it on the Arduino Nano. And then you know the Arduino Nano has 256 kilobytes of RAM. And you could say, okay, let's go with the model that still fits onto my device, but has the higher accuracy. And that would be kind of the workflow we use to develop AI solutions on embedded devices and microcontrollers. With that, I would like to hand over to my colleague Peter, or before we have some questions, yes?
Actually two. The first one, have you also looked into the possibility of training an AI model on another bigger AI model? Like you have this huge model with the input and it's basically working way better, and then you train a smaller AI model on this one, yeah, to make it possible for embedded AI systems.
Do you mean like model distillation, or there's something that as it kind of rings my bell what you're saying. There's a procedure called distillation where you use bigger models and you start training them, and use the output of the bigger models to train the smaller models. It's like teacher-student framework, something like this. Not specifically, but we're looking into all kinds of methods to reduce the size of AI models. I think we've looked at this for image object detection. There was something, but I wasn't really directly involved in, so can't really say a lot. Yes.
If you go 2 slides back.
This one?
Yeah, in the model training and pruning, like you mentioned sparsity. So in the compression, do you use like RSC compression and CSC compression, like that? Like for the compression, so is it like
Yes.
compression to exploit sparsity, like CSC compression and RSC compression?
So it's not about compression itself. It's about finding good heuristics to decide which sections of your network are kind of unimportant. And what you do is during training you set these values to 0. Maybe you have whole structures like channels in a convolution, and you say, okay, this kernel here, this channel, it's not so important, so I set the whole kernel filter to 0, and that's why we see this increase in the sparsity, and we do this multiple times, and at the end you see this drops down to 0. So this is like the step where we actually thin or make the architecture lean by removing the 0 filters, for example. Does this kind of answer your question? I'm not sure.
Yeah, like while deploying that like activations and weights on the microcontroller, so you just ignore the zeros. Like you don't consider 0 values while putting on the ROM.
So there are multiple ways of doing pruning. One is unstructured pruning, and one is structured pruning. And the benefit of structured pruning, what we use here, is that you can actually remove the 0 valued weights. They are no longer in the calculation. Any more questions? At least those of you who will participate in the workshop on resource requirements of AI, they will get more details on the topic. Thank you.